Swayam Prabha. Digital India. Educated India.
We are into the second concept under strain and deformation, which says displacement field and displacement gradient. Okay. Now, we saw that the strain is a measure of deformation. We saw deformation could be change in length, change in angle. We quantified using strain. Okay. That is why the sentence says strain is a measure of deformation. Now, the way in which we discussed strain, either normal strain, shear strain, we said we mark some points, and then remember we discussed how the points move. We had a symbol called variable called u, okay, which represent displacement. Okay. So, we marked some points p, q or r, p, q, and they got displaced to some other positions. Okay. So, which means that the strain depends on the displacement of points in the body. Now, after this discussion on displacement field and displacement gradient, we are going to relate both of them. So, before relating, we will discuss what is a displacement field, what is displacement gradient. Okay. So, to summarize this slide, we first introduced deformation, quantified it using strain, but these depend on the displacement of the points or solid particles, and so we are discussing now about displacement field and displacement gradient. Okay. The word field is known to us right from several classes earlier. Field represents the variation of any property in spatial location. Okay. For example, we discussed temperature field, velocity field, etc. So, just like temperature field, velocity field, pressure field, here we have displacement field. So, moment to look at displacement field, that is the idea that should come to your mind, that it is going to tell about displacement as a function of x, y, z, okay, just like temperature, pressure, velocity, etc. Okay. We come across temperature gradient. Similarly, we are going to discuss about displacement gradient here. Of course, conceptually they are more involved. Okay. The way in which we are going to discuss displacement field and gradient is parallelly. We are going to discuss displacement field, displacement gradient. We are going to discuss hierarchically also. What is hierarchy? Slowly introduce for one dimensional case, then go to 2 dimensional case, then go to 3 dimensional case, that is a hierarchy. So, first take 1D, discuss displacement field and gradient, go to 2D, discuss both of them, similarly 3D, okay, that is the plan. Okay. Now, let us start with the 1 dimensional case. We are going to discuss about displacement field. Okay. What is shown here, of course, a very good discussion from our book by W.D. Means on stress and strain. We can imagine a plate or a wall and then a wire attached to it, okay. And you mark some points on the wire A, B, C, D, and they are at locations 0, 1, 2 and 3. Now, you stretch the wire, and that is what is shown in the second diagram. Now, what happens? The points or particles have moved to some other location, the A, B, C, D have moved to some other location. They have moved to location, A has not moved, in fact, it is just staying in something like attached to the wall, let us say. B has moved to 2, C has moved to 4 and D has moved to 6. Now, in terms of nomenclature, which I have used a few times earlier, the first figure represents the undeformed state or the initial state. The second figure represents the deformed state, because you applied a force and continue to apply the force. Now, in terms of coordinate axis, I am using 2 coordinate axes. X axis, capital X represents the old coordinates, small x represents the new coordinate axis. The points A, B, C, D have in terms of values, capital X equal to 0, 1, 2, 3 for the undeformed state, small x is equal to 0, 2, 4, 6 are the position in the deformed state. Now, how do we formally say point A has not got displaced, but B has displaced from 1 to 2, and then C has displaced from 2 to 4 and D has displaced from 3 to 6. Remember, the scale is same, only the nomenclature of axis is different. What do I mean that by that? You take the same scale, scale cannot change. See, remember, this 0 and this 0 are same, this one and this one are same, the scale is same, only the axis you used to represent the position or the coordinate is different in the old configuration and the new configuration. For old I use capital X, for the new I use small x. Now, what does the third diagram represent? It represents the displacement of all the 4 points of the 4 solid particles. Let us see how does it represent. Point, now here u represents displacement, it is a vector, right now it looks like a scalar, but actually it is a vector. So, u vector for point A, point B, point C and point D. Now, point A has not moved, so it is a null vector, u A is a null vector. B has moved from 1 to 2, so the arrow mark shows a displacement from 1 to 2. C has moved from 2 to 4, so a displacement of 2 units, of course all along the x axis. D, which was at position 3, has moved to 6, so this represents a displacement of 3 units for point D. So, third diagram represents, because we are discussing both, because we are discussing the displacement field, look at the nomenclature here, it says x and x axis are small x axis and capital X axis are superimposed, that also shows we are at the same scale. Okay. So, the third diagram represents the displacement for the different particles A, B, C, D. It shows an arrow from the initial position to the final position. Okay. Let us move on to the next slide, and what is shown here formally is called the displacement field. The displacement field. Why is a displacement field? It shows displacement as a function of position, as a function of position. What happens to displacement field for different particles? Okay, this is what we are going to discuss in the next slide in a more detailed way. Now, the displacement field here use a vector, I have displacement only in the x direction. So, I have not denoted that as ux, displacement in the x direction, just like our velocity in the x direction, here we have displacement in the x direction. Now, the displacement field ux can be represented in two ways. What is that? The displacement can be represented in terms of the old axis, that is capital X axis, or the displacement can be represented in terms of the new position axis or small x axis. Let us see how do we represent. Remember, these are the displacements. Remember, we had 0, 1, 2 and 3. The displacements are same. What is shown above the line are displacements. Similarly, the displacements are same, 0, 1, 2, 3, but the variable or axis with which you relate, that differs. In the left hand side figure, you have related this displacement to the old coordinate. So, you are showing the displacement 0, 1, 2, 3 against the old position 0, 1, 2 and 3. In the right hand side, you are showing the displacement against the new position 0, 2, 4 and 6. So, the independent variable which is different in both the two figures, but the dependent variable, the displacement is same in both the cases. The displacement is same, that cannot be changed certainly, but with which you are trying to relate the independent variable, the position, that differs. It could be the old position 0, 1, 2, 3 or it could be the new position 0, 2, 4, 6. Now, I will use let us say grammatically correct English statement. If I want to explain the first figure, I should say that 0, 1, 2, 3 are the displacements that will happen for the particles at 0, 1, 2, 3, because that is the initial state before you applied the force, that is the undeformed state. Now, we applied the force it has come to another equilibrium state, you are in the final state. Now, if you want to explain using a grammatically correct statement for the right side figure, I should say these are the displacements that has occurred for the particles which were at 0, 1, 2, 3 or which are currently at 0, 2, 4, 6. Okay. So, in one case displacement that will happen, in other case displacement that has happened. Now, you can, what does these two figures tell you? The displacement field, in this case just u x, can be related as a function of capital X or can be related as a function of small x. So, u x is equal to, if you want to relate these two, what is the relationship? Very clear, u x is equal to capital X, 0 equal to 0, at 0 you have 0 displacement, at 1 you have displacement 1. So, just u x equal to x. Right hand side, it is the displacement is half the new coordinate position. So, u x is equal to half of small x. For 0 you have 0, for 2 you have 1, for 4 you have 2. So, the relationship which connects the displacement and the new coordinate is u x equal to half x. So, as I told you, the independent variable either is capital X or small x, the dependent variable is the displacement, that is same, the functionality which you express or the function which you use to express or the axis which you use to express, that can change either the old coordinate or the new coordinate. Okay. Now, the title of this slide says displacement gradient. We are going to define displacement gradient. Okay. Let us define that. Difference in displacement of two adjacent particles divided by initial or final distance between the same particles. Okay. Okay, let us understand this clearly. It says two adjacent particles. As usual, why two adjacent particles? They are very close to each other. We get a point definition of displacement gradient everywhere, that is a common theme throughout. All our equations, all our variables should be valid at a point, definition should be valid at a point. So, we consider two adjacent particles. Of course, here as per the diagram it may be slightly away, but theoretically considering two adjacent particles. And let us say for example, we are considering particles which were at 1 and 2, their displacements are 1 unit and 2 units. Now, difference in displacement of two adjacent particles, the displacement of particle at 2 is 2, which was at 1 is 1, the difference in displacement is 1 unit. Now, what is the denominator? Initial or final distance between the particles. So, now there is a possibility of two choices. The distance between the two particles in the old configuration is 1 unit, but in the new configuration is 2 units. So, now same definition, delta u x by delta capital X is 1, delta u x by delta small x is half. Let me repeat, we are considering two particles which were at 1 and 2, their displacements are 1 and 2. So, the difference delta u x tells difference in displacement, that is 1. Denominator, the first case we are taking the initial distance between the same particles, the initial distance between them is 1. So, giving us value of displacement gradient of 1. The denominator we are using delta capital X, denote distance between the initial distance between the particles. Second alternative is numerator, there is no ambiguity, represent difference in displacement of two adjacent particles, but denominator I take the distance between the final distance between the particles, I take the final distance between the particles which is 2 units. So, I have 1 by 2 as half. The two values of two different ways in which you can express the displacement gradient. Now, the small very small animation tells you to helps you understand better. Okay. Let us imagine like on the same road we have two persons standing and they are initially at these locations, one represented by blue circle, other represented by the orange circle. So, these are their initial position and this is the distance between them in the initial configuration, let us say, and both of them are the same line. Just for understanding I have shown separately. Now, let us say they start walking and then after the same time, let us say one walks much faster, the other walks slower, and these are the final position of the two persons. Now, to evaluate this, let us say you want to evaluate the displacement gradient for these two persons. This first person has, this is a displacement of the first person and this is a displacement for the second person. The numerator is difference between these two lengths, these two distances. Now, denominator, either you can take the initial distance between them or the final distance between them. Okay. That is the analogy between, here we are discussing particles, little bit easier to understand. If you take two persons, they are at two different locations, they start walking, depending on the rate at which they walk, they are at two different positions, and the first person displacement is so much, second person displacement or the distance walked by the person is so much, that difference is the numerator. Now, divide by the distance between them, you take the initial distance or the final distance. Okay. So, what we have introduced is a displacement field. Why is a displacement field? In this case, it is only one dimension. So, ux only is considered, either it is a function of capital X or small x. We said displacement, any field is a expressing a property or a variable in terms of xyz coordinates. In this case, only one component ux as a function of only one variable, either capital X or small x. Now, we have been telling capital X, small x, etc. That of course is difficult to understand and take forward also. What we are going to discuss is a condition under which we need not differentiate both the definitions of the displacement gradient. So, that we need not worry about either we consider capital X or small x. When does that happen? Formally, what we are going to discuss is called infinitesimal strain. Let us see what is it, what it is. We take the same case of, let us say a thread attached to point A. Now, we apply a force, this point B now gets displaced, point A is at the same position, but point B, displacement of point B is very small, it just gets displaced by 0.001. Now, if you look at the difference in displacement, what is that? This displacement is 0, point B got displaced by a small value 0.001. So, difference in displacement is 0.001. Okay. B got displaced by 0.001 units, A did not get displaced. So, difference in displacement is 0.001 minus 0 is 0.001, that is a difference in displacement. Now, what is the distance between them? In the initial state, we took let us say a wire of thread of length 1 unit, that is a distance between A and B. Now, in the final configuration, the distance between them is 1.001. Okay. Specifically, we are taking going up to the third decimals, you will understand why do I do that. So, initial distance between them is 1 unit, the final configuration the distance between them is 1.001. Displacement does not depend on whether you take initial distance or final distance, that is anyway 0.001. Now, we will calculate the displacement gradient based on the two options we have. The first case, delta ux by delta capital X, delta ux is 0.001, the difference in displacement, denominator is 1.000, to be very specific, we have taken up to 3 decimals. The value of the displacement gradient is 0.001, option 1. Coming to option 2, we have delta ux divided by delta small x. Now, the difference in displacement is 0.001, certainly same as the first case. Now, we have to take the final distance between the two particles, that is which is 1.001. If you divide, the value of displacement gradient is 0.000999, and this is roughly same as this one. So, what do we conclude? If the displacement is very small, if the strain is very small, then both the derivatives are same, and we will use our very familiar derivative delta ux by delta small x, or in terms of partial derivative dou ux by dou x. Why? Eventually ux is going to vary with x, y, z, etc. So, we have to represent using partial derivative. and that is why we call this as infinitesimal strain. This is an assumption under which we are going to work throughout our solid mechanics. We will discuss more about this later. Right now the conclusion from this slide is that if the displacement is very small, if you want it in terms of normalized way, if the strain is very small, if it is infinitesimal, then either you can work in terms of this definition of the displacement gradient or this. We are very familiar with the small x and we are going to work with dou u x by dou x. Okay. Now, let us move on to same discussion extended to 2-dimensional case. We will discuss displacement field, displacement gradient. Now, what is shown here is a plate. The red dots show the some points identified or particles identified in the plate in the undeformed configuration, the initial state. You apply a force, it gets deformed, it reaches another equilibrium state. Now, whatever points you identified earlier have now got displaced and those are shown as the blue dots. So, something like the plate which was of course little more exaggeration, it was which was like this, the red one have become something like this. Okay. Okay. Now, if you look at this, the case of a 2-dimensional displacement, we have taken this example to illustrate this illustration to discuss 2-dimensional displacement field. Now, because it is 2D, we will have to consider ux and uy. What is ux? Displacement in the x direction. Now, let us take an example. Let us take these particles around this region, around in this horizontal line. If you see these two particles, the same particle in the initial state and final state, it has got horizontally displaced, there is a ux. If you take these two, the ux, there is a ux, the displacement in the x direction is different from these two points. Now, as you go along the x axis, the horizontal displacement or ux keeps increasing as a function of x. So, ux changes with x. Remember, ux is displacement in the horizontal direction along the x axis. So, the difference, the x coordinate distance between these two dots represent the ux value. That ux value keeps increasing along the x axis. Now, let us take particles around this vertical line. Now, you have to, if you look at the, once again focus on the x displacement, there is a small x displacement and then slightly more x displacement, slightly more. So, the x displacement is increasing as you go along the y direction. So, ux changes with y as well. Okay. Ux represent displacement in the x direction. In this example shown, it is varying along the x axis, it is varying along the y axis. Specifically in this example, they are increasing along x axis, increasing along y axis. Okay. So, ux is a function of x comma y. It is analogous to, because they discuss about fluid mechanics and so on, it is analogous to the x component of velocity varying along x direction and y direction. Okay. X velocity seems easy to understand because it is displacement, because we are not very familiar with that, slightly difficult to get along with it, but just tells you the x direction movement of a particle which you are focusing, and just difference in x coordinate gives you x displacement. Now, let us talk about the y displacement, displacement in the y direction, which is uy. Now, what should you consider? Let us consider the particles in this region along this horizontal axis. Now, I want to focus on the vertical displacement, which means that I should consider the difference in the y coordinate. Here there is hardly any vertical displacement, but now if you see, there is a vertical displacement between the red and blue dot. That vertical displacement is more here, still more here. So, the vertical displacement increases along the x axis. that is what we are going to say next. Uy changes with x. So, uy increases with x. So, vertical displacement is a function of x coordinate. Now, if you focus let us say particles along around this region, then considering these two particles and there is no displacement in the y direction. If you consider these two, remember they are the same particles in the initial state and final state. So, if you consider the red and blue dots, there is y displacement. If you consider these two particles, there is once again y displacement, it is more than the earlier set, and this y displacement keeps increasing as you go along the y axis. So, uy changes with y as well. So, the vertical displacement changes along the x axis, vertical displacement changes along the x axis, vertical displacement changes along the y axis also. Uy as a function of is a function of x comma y. Combining these two, the u vector can be expressed as ux I vector, uy j vector. Ux is a function of x comma y, uy is a function of x comma y. This is similar to a velocity field. V vector is equal to Vx x comma y I plus Vy x comma y j. Okay. So, what we have seen is an example for a displacement field in 2 dimensional case, where we have both displacement x direction and y direction, both of them vary in x and y direction. Okay.